Okay, in part 2 of 7.6, we're going to be talking about another type of function, a logarithmic function. Okay, and a logarithmic function is going to be ultimately highly related to an exponential function, and they're going to be related by this equation right here. Okay, if we have something of the form that's y equals log base b of x, that's going to be equivalent to the exponential b to the y equals x. Okay, and so if we have a function that looks like this that has a log in it of some base, okay, we call that a logarithmic function with base b. Okay. And again, the key issue here on going back and forth between exponential form and logarithmic form, because we're going to do that quite often, is to recognize that when we have it in this form, if you will, we have a base and an exponent, as we know. Okay, the exponent goes on the left, the base goes here beneath the log, and then the argument goes here. So this is the argument of the logarithm. Okay, that becomes the other side. So when we want to change from logarithm to exponential, what I usually say to myself is this. I rewrite the sentence as base raised to the other side equals the argument. Okay, I say it in words as opposed to remembering the symbols. I always say the base to the other side equals the argument. Okay, so if we were to graph, for instance, a logarithm function, okay, what we would want to do is we would want to graph its equivalent exponential function. Okay, that means that we'd have 2 to the y equals x would be the equivalent to that based on our definition. And what we'd want to do to get the xy points that we're going to plot is we'd want to put numbers in for y instead of in for x. So normally we put numbers in for x and solve for y. In this case, we'll put numbers in for y and we'll solve for x. So if we do that, if we put in -2, -1, and so on, we get the following x coordinates here. And if we plot those ordered pairs, we get the general shape like this. Okay, so any logarithm function is going to have this general shape. And just like an exponential function went through 0, 1, okay, a logarithm function is going to go through 1, 0. Okay. Now, if we look at this temperature data over here, you can see that it has the shape of a logarithm function. Okay. All right. And what we're going to be asked to do with that is we're going to enter this data and we're going to get what we call a natural logarithm regression formula for it. Okay. So just like I did in the previous one, I'm going to go ahead and do stat edit, and I'm going to put my data in there. We have times of 10 through 60 here, so we're going to go 10, 20, 30, 40, 50, 60. Delete the 58. And then my temperature data is 19, 29, 34, 38, 41, 43. And what I want to do is I want to do logarithmic regression here. So I'm going to go stat, calculate, and I have lnreg. Instead of linreg, it's lnreg. It's going to be the natural log regression. It's a different special type of logarithm. We'll talk about it a little bit more in a minute. But ultimately it is of the form a plus b ln x. Okay, so we have our a and we have our b. Okay, and so therefore we can write an equation. And just like they showed here, we're going to express it in function notation. We're going to use it to figure out the answer for 50 minutes. How well does it resemble the actual increase? Okay, so in writing it into the f of x form, again, they said nearest 1 decimal place, so we're going to go -11.6, 13.4, plug them in appropriately, okay, and then that right there would be our model. If I put that in my y equals to make a prediction, similar to what we've done with linears and exponentials, okay, we can go ahead and plug in 50 for the time here. We can either do it by typing it in or we can use our table again. So I'm going to go to my table. I'm going to delete these two and then I'm going to type in 50 and see what my answer is. It says it's 40.8. Okay? And so since the actual temperature increase is 40, 41, if we did it to the nearest whole number. Okay? And what we want to do is compare that. Okay? We ultimately get 41. Okay? If you go back to the original data, okay, the original data on the graph that we started with, it shows 41 after 50 also, so that model does a very good job of giving us the answer after 50. So 41 is the exact answer. Okay. Now, the other type of modeling that we're going to do is with the quadratic function, so another function that we've had some experience with in Algebra and Algebra 2. Okay, we can do the same thing with the quadratic equation here, recognizing that when we do have one, the graph of it is a parabola. Okay, the vertex of the parabola is the lowest or highest point. Okay, we know that we've seen quite a bit with parabolas. Okay. We know that there is an axis of symmetry that goes through the vertex, whether it opens up or down. Keep in mind that the a value being greater than 0 means it's a parabola that opens up. If the A is less than 0, it's going to be a parabola that opens down. So those are just some features of parabolas that we already know about. And then another thing that we know about parabolas is if we are given an equation and we want to find the vertex, we can use the formula for the x-coordinate of the vertex. We can go negative b divided by 2a. The coefficients on x squared and x tell us what the vertex is. They tell us the x-coordinate of the vertex, and of course, remember, we have to take the x and plug it back into the equation to figure out y, and that would give us the y-coordinate of the vertex as well. Okay? So a couple things here on graphing quadratic equations. If we're given an equation to graph, okay, we determine whether it opens up or down. Okay, we'll find the vertex using the formula. We'll take what we find for x and put it back into the equation to find y. Okay, and then we'll find any x-intercepts. Okay, by replacing y or f of x with 0, and then solve the resulting quadratic equation. Remember, we do that either by factoring or by using the quadratic formula. Okay, we can find the y-intercept by replacing x with 0. We'll plot the intercepts in the vertex, and then we'll connect these points with a smooth curve. Okay. Now, if that doesn't give us enough points to get a good picture of it, then we can really pick any points we want to. We can choose our own x's and figure out what y equals, and then go ahead and graph. So, an example. Negative x squared minus 2x minus 3. We know this opens up because it's got a positive coefficient in front of x squared. The a is 1, which is positive. Part b, we're going to find the vertex, so we'll do negative b over 2a. So I did that right here. The opposite of b is 2 over 2 times a, so we end up with 1. If we plug the x-coordinate back in there, we get 1 minus 2 minus 3, which is negative 4. So therefore we have our vertex. Okay. So if we have our vertex, we're next going to find the x-intercepts by putting 0 in for x. In this case, we're able to factor, which is convenient because we get a couple of nice factors which give us 2 nice zeros. So 3 and 1 are the 2 x-intercepts, so we can plot those 2 points as 3, 0 and negative 1, 0. Actually, should have a negative sign right there. So 3, negative 1. So those 2 are going to be our x-intercepts. Okay. We will then find the y-intercept by putting 0 in for x and solving for y. And so if we do that, we get negative 3. So 0, negative 3 is a point that's also on this parabola. So at this point, we have 4 different coordinates that we can plot. And if we plot those 4 points, okay, we can get a pretty good general picture of what the parabola looks like, knowing that it looks like a smooth curve. And we need to make it, of course, look like a parabola. And make sure when we're graphing these, we graph carefully. I've seen parabola graphs that look like this. Okay, that's not a parabola. Okay, so don't do that. This is not a parabola. Okay. So don't do that. Make sure it actually looks like a parabola when you graph. Okay. Alright, so let's talk about modeling. We can model data just like we did with our other types of functions. If we have years since 1980, we're going to go ahead and plot our points here. We'll go stat edit. We're going to do years since 1980, so 0, 5, 10, 15, 20, and 25. And are going to be the x's here, years since 1980, and the x direction, the y coordinates are 2.6, 2.3, 2, 2.1, 2.5, 2.8. And just like our other modeling problems, if we were to look at it in scatter plot form, it does look like it has maybe a parabola shape. Okay, so the best method to find an equation for it would be to use what we call a quadratic regression. So we're going to go ahead and go back to the calculator and hit stat calculate. You have quadratic regression in your list also, number 5. And if we do the quadratic regression, it gives us a, b, and c, okay, which go into the equation ax squared plus bx plus c. So ultimately, we want to write it as a function with 3 decimal places. Okay? And then ultimately with that, we're going to figure out how does it do for 2005. Okay? So I'm going to go ahead and put that into my y equals so I can use it to make predictions. So I'm going to go 0.004x, wrong button, 0.004x squared minus 0.094x plus 2.607. And with that said, we're going to do the prediction for 2005. So if I were to go to my table again, 2005 is going to be 25 years after 1980. So it predicts 2.757. And if I get that 2.5757, okay, the actual number that was on the data was 2.8, so it does a very good job. Okay, so it models extremely well for 2005. Okay, and of course, if we wanted to know another year, like say down the road 2025, okay, and then we could put a 45 in there and we would see what that predicts, and that would predict 6.477, and that may or may not be a good prediction that far down the road, okay, but ultimately we can use this to predict any year that we're asked for. Okay. Alright, so ultimately let's go ahead and summarize all the modeling that we've dealt with so far here. Okay, if we have a set of data points in the scatter plot, if we look at the scatter plot and they lie on or near a line, okay, then we're going to want to use linear regression. Okay. If we're starting to increase more and more rapidly, then we're going to want to use exponential regression. If it's increasing, although the rate of increase is slowing down, okay, then we're going to want to use a logarithm function. We'll use logarithmic regression. If it's decreasing then increasing, we're going to want to use a quadratic function, quadratic regression we have in our calculator also. Or if it's increasing and then decreasing, okay, a parabola that's upside down, if it looks like, we're still going to use the same quadratic regression key, okay, but it's going to end up having a negative a value, okay, which makes sense because the parabola that opens down is going to have a negative a value. Okay. So at this point, if we're given any scatter plot, we should be able to judge, okay, by looking at the graph, okay, which one of these would be the best model to fit that particular data. And once we make that decision, we can write the equation with our calculator, and then we can use that calculator to make predictions.